Good day. Today's lesson we're going to study Oceanography Part 2. It's a continuation of the first lecture. We're learning about the marine habitat and and how they affect the organisms that live there. If you take a look at this image, that is an image of the loop current. Loop current is a warm water current that flows through the Gulf. You can also see some eddies, which are located west, in the west part of the Gulf, that spiral off the loop current, and then the loop current then passes back through the Straits of Florida and joins the Gulf Stream. So that is what influences the Gulf, the currents. So without further ado, let's begin the lecture. Solution chemistry is our first topic because water is a solution, salt water. So solution chemistry would be our first topic to look at. Now, water itself, H2O, is a polar molecule. If you look at it, in the image below, you can see how hydrogen and oxygen share their outer electrons. The electrons are called valence electrons, thus making a molecule. Water has a +8 in its nucleus. You can see +8 there, and right there's the +8. Hydrogen has a +1, so +8 is a lot more powerful than +1. So the oxygen right there holds the electrons tighter than the hydrogen, making it a polar molecule. Di meaning two pole, or bi meaning two pole. Right there, you have a partially negative pole and a partially positive pole, uneven sharing. So that uneven sharing means water attracts to itself. That's called hydrogen bonding. It's really not a true chemical bond, but it is a electro attraction between the negative oxygen, positive hydrogen. It explains water's unique properties. For one, water is a tiny little molecule, and it would be a gas if it wasn't for this, but this attraction holds the molecules close together, so it allows water to exist in all three states. It also means water, when it freezes, forms a less dense object because it forms a crystal, and in those crystals you have air spaces. You can see here large air spaces within the crystal. So the hydrogen bonds make it form a lattice, and therefore ice floats on top of a more dense liquid water and allows life to flourish under the ice. Now the calorie is how we measure energy. The gram calorie, or small c, is one calorie is the energy it takes to heat it up 1 degree, whereas the calorie that we're most familiar with, the capital C, or the kilocalorie, is a kilogram of water, or 1,000 calories. And we say this because that hydrogen bonding makes it difficult to vibrate a water molecule. When you raise temperature, it vibrates. It's held in that form with the hydrogen bonding, so it takes a lot of energy to heat up water and cool off water. And that's why water moderates climate, distributes heat throughout. So we call that heat capacity, and you can see right here, liquid water takes a lot more heat to raise 1 calorie or 1 gram. So water's 1. Take a look at granite and sand, which our beaches are made of, 0.2. So the land heats up a lot faster. It only takes 0.2 calories to heat up land. It takes a full calorie to heat up water. Now because of that, during the day, land heats up, air rises, and you get a afternoon sea breeze. Take a look at this. The water, air sinks, air rises, you get a convection cell. See this right here? That's our afternoon thunderstorms on the coast. Every afternoon, thunderstorms whip through during the summer because of this sea breeze effect. Then in the opposite occurs at night, land cools off faster, so the winds reverse and you get cloud and fog out over the Gulf every night. So that's our sea breeze, land breeze. That's how it affects local weather, local climate. Now, water, like we said, is a solution. Water is polar, so it dissolves salts. The salts dissolve in the water, and that is what a solution is. Things dissolved in other things. It's a homogeneous mixture, meaning that if you had a glass of seawater, the top and the bottom would be the same, homogeneous, the same throughout. Water is a polar solvent, and things that dissolve in water are hydrophilic, water-loving. Now, nonpolars float on the water if they're less dense, like gas right there, marina, oil slicks. They don't mix with water because they're not polar. Now, seawater is a mixture of over 70 elements, but really only 6 make up most. Then there's trace elements. So seawater is water and then 3.5% dissolved solids on average, 3.5% dissolved solids. So it's 96.5% water. The most common dissolved chloride, the chloride ion. Sodium second. So sodium chloride is what we call salt, even though there's other salts. And so chloride is the most commonly dissolved solid, followed by sodium. The solubility is what dissolves in it. It's like chloride and sodium dissolve in it, salts. Gases, that's what's important for us marine biology people. Oxygen dissolves in the water. So a fish that is using its gills to extract oxygen is not taking the oxygen from the H2O because that's bonded. It's no longer oxygen, it's water. It's taking dissolved oxygen out. The salinity then is 35 parts per thousand. That's the most common unit, parts per thousand, PPT, or a percent with an extra zero, because 1,000 has one extra zero over 100, or 3.5%. That's most of the ocean. At the surface, you can have hypersaline water, saltier, Dead Sea, Mediterranean, where you get little rainfall, a lot of evaporation. But more commonly, we get brackish water, where it's a little more dilute than 35 because of rivers, input. Our brackish, Tampa Bay is a little bit brackish because of all the runoff from not only the rivers, but every time it rains and from land. So brackish water is a mixture of fresh and salt water. That is very common. The global map of salinity, you can see around the coasts, less saline. In the center of the ocean where you have all evaporation and no runoff, more saline. And at the equator, you see it's blue right along the equator, right along here, this is blue. That's because the equator gets a lot of rain. These areas get less rain. All the desert, Sahara Desert here, dry as a bone, so all this air is dry, much saltier. And of course, all of the runoff making coastal areas saltier. Tonicity then, tonicity, this is important to our marine organisms. Most marine organisms are hypotonic, meaning their body tissues have the same salinity as the surrounding water. Okay, that's isotonic, my apologies. When you have very salty water, say a freshwater fish in a saltwater environment, the water is pulled out of the cells and the cell dehydrates. So salt water forces dehydration for organisms that are not as salty. Like when you eat popcorn, you get very thirsty. That dehydrates you. The dissolved gases are important. We mentioned that oxygen is pulled from the seawater. The most common gas is nitrogen, though. Nitrogen is the most common gas in the atmosphere, and it is also the most common gas dissolved in water. Carbon dioxide is an important gas because it's used for photosynthesis as well. So like we said, nitrogen, 78%. It's abundant in seawater. When humans go too deep, we get what's called narcosis. A little bit extra nitrogen gets in our blood, and nitrogen, N2O is laughing gas. So you get a bit of a rush with too much nitrogen dissolved in your blood. Oxygen is the important one. Photosynthesis, respiration. Photosynthesis adds it, respiration removes it. The colder the water, the better it dissolves oxygen. So oxygen is abundant near the poles, near the equator. You can have minimum oxygen. And also at depth, there is the middle layer of the ocean. When we look at ocean layers, doesn't get much mixing. It has an oxygen minimum zone. And then deep ocean has plenty of oxygen because it's cold water. It's nutrient rich from the surface. It sinks Arctic water, sinks a lot of oxygen, but it's trapped in that deep layer. So oxygen distribution, you can see that oxygen is more abundant in the colder water, Arctic, Antarctic, and it dissolves less in the warmer water where you're in equatorial regions. The pH is important. pH is defined by the abundance of hydrogen, which makes it acidic, hydrogen ion, or hydroxide ion, which makes it basic. Water, pure water, is exactly H2O, same amount of hydrogen as hydroxide, H2O, 7. Anything lower than 7 is acid. Anything higher than 7 is base. Seawater is slightly basic. That allows calcium carbonate. Carbonate is a buffer. When you get a tummy ache, you take Tums. That's carbonate. Organisms use that to make shells. So the whole calcium carbonate cycle is keeping the ocean's pH stable, calcium carbonate. Organisms are abundant shelled organisms. So shells dissolve when they die. Shells are created, so that's called a buffer. It keeps the pH stable, mildly alkaline. So you can see here on the pH chart, pure water is 7, seawater is approximately 8, and other acids and bases. Carbonic acid, when we make carbon dioxide, and climate change, big issue, not really talked about acid rain. That was bigger in the 70s before climate change took the stage, where oceans stay pretty stable because of the carbonate cycle, even though we're starting to see some flux, which is dangerous because then these organisms are at risk that use carbonate. Food chains could be disrupted, but lakes were building up acidity and it was killing the fish, the salamanders, they lay soft eggs, very pH sensitive. So industry releases carbon dioxide, it forms carbonic acid. When it mixes with water in the clouds, rains down acid. That's what acid rain is. It wears away at marble and granite structures. So bridges, weathering, and erosion occurs quicker. It changes the pH of freshwater environments. So we saw biodiversity take a hit. And now we're starting to see oceans take a hit. Remember, carbon dioxide spiked in the 1900s when, even in the 1800s, but really we started to see the repercussions in the 1900s from industry. So carbonic acid is acid rain, and it changes the pH and changes ecosystems. And again, buffers, like I said, calcium carbonate is the buffer. It's the buffer in us too. We have calcium carbonate, we have bones, and that moderates our pH, our internal pH, which is slightly basic as well. So the calcium carbonate in the organism shells have a cycle to keep ocean pH stable. The deeper you go, the greater the pressure. We know that. So every 33 feet or about 10 meters, you increase your pressure by one atmosphere. The whole atmosphere pushing down on you is sea level. 33 feet down, you're at 2 atmospheres. 66, 3 atmospheres. And of course, that pressure, we get susceptible because our bodies are adapted for 1 atmosphere. So you have a certain amount of oxygen in your blood, you have a certain amount of nitrogen in your blood at 1 atmosphere. When you pressurize it to 2, your blood have more oxygen, more carbon dioxide. 3, more oxygen, more carbon dioxide, more nitrogen. Then you come up too fast and that has nowhere to go, so it turns to bubbles. And that's called the bends. So changing your depth too fast causes the dissolved gases to carbonate you, for lack of a better term, like a soda. Organisms like a fish, you catch it, you reel it up too fast, its insides pop out of its mouth. It's gas bladder, because you change its pressure too quick. So organisms are adapted for their pressure and they can't change it as quick as well. The ocean is made of layers. That intermediate water you see, that's where your oxygen minimum zone is. Surface water is sunlit, changes temperature, changes salinity due to the weather, makes about 2%, but most life lives there because of the light. Light only penetrates a couple hundred meters at most in the clearest water. Then you have what's called the dysphotic zone, a little bit of light, not enough for photosynthesis. The intermediate water, so you're not getting oxygen added because there's no photosynthesis. It's stagnant, it's not mixed. So you have an oxygen minimum layer. Below that, you can see the deep water, which comes from Antarctic bottom water, North Atlantic deep water. That's what the acronyms are. They have decent nutrients and oxygen. They mix, although it mixes over centuries, it still gets mixed, so it's being replenished. But the intermediate water is where the thermocline is. You got warm surface water, cold deep water, so it's a temperature drop. The pycnocline, density drop. Cold water is a little more dense. And you have the halocline, salinity change as well. So the surface water fluctuates in salinity. The deep water is 35 parts per thousand. The surface water fluctuates in temperature. The deep water is 4 degrees Celsius. 4 degrees Celsius, maximum temperature density. And then the intermediate water is about 18% of that water mass, oxygen minimum. All right, so density is what that circulation is called thermohaline circulation. It's due to density, and density is determined by temperature and salinity. So density, mass over volume, changes with temperature and salinity. The denser water sinks. So the surface, like we say, only 2%, least dense. The middle, intermediate, pycnocline, change in density, 18%. And then the deep is 80% of the ocean, no light, dark, cold. There's an image showing you the layers and their depth, and a little explanation next to it. Back, we do have a typo. I will fix it. The deepest part averages about 4 degrees centigrade. 4 degrees centigrade. So sunlight only illuminates the top part of the ocean, only the upper 200 meters. Red light only makes it down a few meters. So you go past 10, 12 feet, there's no more red. Everything looks green and blue. Deeper, deeper, deeper. And then finally, blue penetrates the deepest, deep blue sea. So you start to lose colors. And of course, this determines what photosynthetic pigments are best. Because if you're losing light, that light cannot be used for photosynthesis. There's the zones we mentioned, the euphotic, dysphotic, and aphotic zone. Photic zone, plenty of photosynthesis, 200 meters. Dysphotic, big eyes, a little bit of light, no photosynthesis. And then aphotic, bioluminescence galore because there's no light being produced any other way. All right, so in the surface, you have much more productivity than anywhere else because of the sun. Seaweed, algae, they are the main photosynthesizers. The transition area, great pressure, so only special suits or special apparatus can make it, so it's tough to explore the transition area. The life living there, big eyes, makes its own light. Some of the cooler examples, giant squid, glow-in-the-dark jellyfish. Notice there's not rigid skeletons there because, mostly flexible body because of the great pressure. And then, of course, in the deep zone, organisms glow bioluminescence. Bioluminescent organism, the anglerfish, the blobfish uses hydrostatic pressure to give it form. So the water pressure would give it a form when you pull it up. It's just a lump of mush because it doesn't have the pressure. So when you go across the ocean floor, near the continents, it's shallow. We call that the continental shelf. The slope is the deep drop-off. Those are all made of granite, the same as the continents. That sand, that granite, heats up fast, cools down fast, same thing. Then the abyss, the deep floor. Plain trench, deep sea trench. So that's what the ocean floor topography generally looks like. Most life here, continental shelf, that's where most life lives. Now no sunlight below here, so middle area, less life, and then the ocean floor has some life on it as well. So you can find life throughout, but it's sparse. Here, the majority, 95% of life lives in the shelf area. So continental margins, that's the continental shelf area. Then the basin, we call that the abyss. The continental shelf, then a slope down, and then sediments build up, continental rise. That's really nutrient rich. A lot of oil deposits at the base of the slope. Sediments build up. Here's your topography, wide shelf, sediments down here, deep slope, abyssal flow. Hydrothermal vent, spewing out chemicals used for chemosynthesis. Seamounts are old, extinct undersea volcanoes. Guyot's have flattened topped. They're called seamounts and guyot's. Guyot's flattened topped. So when you look at the marine environment, the benthic zone is your ocean floor. Okay, benthic, ocean floor. The littoral zone right here, littoral zone, is intertidal, neritic, over the shelf, oceanic, over the deep. Bathyal, slope, abyssal, hadal, deep sea trench. Euphotic, lots of light, dysphotic, not much light, aphotic, dark as it gets. So these are just terms. If you ever see the term abyss, that means ocean floor. You ever see the term pelagic, that means over the ocean floor. If you see the term oceanic, it means over the ocean floor. So pelagic and oceanic are similar. If you see the word neritic, over the continental shelf. Littoral, in the tidal area. So this is just terminology and an image to hopefully help you visualize where each is. Now in our littoral zone, you get a splash zone, very sparse tides every day, almost always covered. So The littoral zone, high tide, low tide, high tide, low tide. And so different things live there. They live in layers. Life layers out because some things, like filter feeders, always need water, so they have to live here. Some things can crawl around, so they can live throughout the littoral zone. Some things can dry out and then rehydrate, like seaweeds can live in the upper littoral zone. So the littoral zone has various bands of life. The neritic zone over the shelf, 90% of ocean life, warm, sunlit, photosynthesis. You can go out 200 miles and still be in the neritic zone in some areas. Other areas, you can go out 10 miles and the neritic zone's gone. You're over the pelagic zone, you're over the deep ocean. Just depends on coastal topography. The oceanic zone is over the deep, big blue. The bathyal zone, bathyopelagic, that's the bottom. A bathymetric map is a bottom map. That's as deep as it gets. Bathyal, down that slope. And abyss, the ocean floor. Hadal is in a trench. So that's as deep as it gets, literally. Briefing you on the marine lifestyles. That's an image I took scuba diving of a stingray, ambush predator, demersal fish, lives on the seafloor, eyes on top of the head. So if something swims by, you can get it. It's well camouflaged. But plankton is a Greek term meaning drifters. Planets drift too. So in astronomy, the planets are plankton, literally. Plankton are organisms that drift on the currents. Phytoplankton are photosynthetic. Zooplankton are heterotrophs, they eat. Holoplankton always are plankton. Meroplankton are larvae or spending part of their life as plankton. So that's the plankton. Benthic, bottom dwelling, benthos. They live on the bottom. Some are attached, some can crawl, some can dig, but they live attached. And nekton are our swimmers. So nekton swim. Takes a lot of energy to swim, so you have to have a pretty big body. They're the rarest. Takes biological energy to swim. That's with the nekton.